Oh, okay, so let's start. I hope you can hear me. So today we are going to look at this paper for which I've sent you the link in the chat. So this paper, it might not be a bad idea for you to download it and display it on your own screen so that even if the Wi-Fi stops working or something, you will have the paper with you and you can look at your copy. So what we are going to do today is a sort of generalization of what we did a couple of lectures ago. So a couple of lectures ago, we had a field F. Yeah, you see, this is the problem with pencil. It doesn't work. So yeah, let me say it in words. A couple of weeks ago, we had looked at a field F and a prime P, and we were considering all separable extensions of the field, which were of degree P. And when you take the Galva closure, the Galva group is solvable. We had called such extensions solvable primitive extensions, right? Not solvable primitive, solvable extensions of degree P. So this primitive is what we are going to look at today. It's primitive here. So let's go slowly one by one. And so let's fix a field F. And I'll fix also a separable algebraic closure, F tilde of F. I'm not calling it F bar because F bar will perhaps be used for something else. And F bar is usually the notation for the algebraic closure. We are not taking the algebraic closure, we are taking the separable algebraic closure. And all our extensions of F will be inside this F tilde, which is to say that they are not only going to be algebraic, but they are also going to be separable over F. Okay, so this is our F and F tilde. So all extensions of F appearing below will be contained in F tilde, and therefore they'll be algebraic and separable over F. Now, here is the important word primitive. This is an extension of F of degree strictly greater than 1, such that there are no intermediate fields between F and E. So F is given to you, that is fixed, and you're looking at separable, finite separable extensions E of F, which are of degree 2 or more, which are distinct from F, but they are such that there is no intermediate extension. There is no field which contains F and which is contained in E. Now, obviously, if the degree of E over F is prime, then it's going to be primitive in this sense. But the converse doesn't have to be true. We will see later that there are many extensions which are not of prime degree, but which are still primitive. So this is a very important notion, that of a primitive extension. Now, sometimes the word primitive is used in a slightly different, with a completely different meaning. That is when we talk about a primitive element in a finite separable extension. That's an element which sort of generates that extension. We are not using that meaning. We are not using the word in that sense at all. This is the sense in which we are going to use it, primitive, and that's the sense in which maybe Galva had introduced this word. So It's a very simple notion. I mean, in this, it has something to do with primes in the sense that a prime is a number which doesn't have any, it should not be equal to 1. It should be strictly greater than 1. And it should not have any divisors other than 1 and itself. Similarly, a primitive extension is one which is not equal to f itself, but which doesn't have any intermediate extensions apart from, of course, f and e themselves, right? So this is what a primitive extension is. That's the definition. Okay. Now I recall another definition which we might have already which we have already come across actually, and that is the definition of a solvable extension. So what it means is, again, E is a finite separable extension of F. Then we can talk about E hat. E hat is the Galva closure of E over F. Now, given any separable extension, it has a Galva closure, which means it's the smallest extension which contains E. That's all. I mean, it's the smallest, and which is Galva over F. It's the smallest Galva extension of F containing E. That is the definition of the Galva closure of E. And once you have a Galva extension, you have the Galva group G. Now, if that group is solvable, then we say that the extension E itself was solvable. So that's something which we have already come across in the context of extensions of degree P, separable extensions of degree P. We have called them solvable if, when we take the Galva closure, the Galva group is a solvable group. It's the same definition here as well. That definition didn't depend in any way upon the fact that the extension that we were considering was of degree P. It applied to any finite separable extension. And that's what we are looking at now. Okay, so E hat is the Galva closure of E over F, and we call it solvable. We call E solvable if the Galva group of E hat over F is a solvable group. Now, here's the important thing. We had stated and proved Galva's theorem, which sort of classified extensions of degree P which are solvable, right? What Galva proved for primitive extensions, which are a generalization of extensions of prime degree, is that if you have a solvable primitive extension, so it should be both primitive and solvable, right? These two definitions at the same time. Then the degree of such an extension is the power of some prime number. It's a prime power. This is what contained in what is called Galva's second memoir. He wrote one very important paper called the first memoir, which contains basically the elements of Galva theory and the theorem that an extension is solvable by radicals if and only if its Galva group is a solvable group. So that theorem, we have converted it into a sort of definition. We are only looking at extensions for which the Galva group of the Galva closure is a solvable group. But the second memoir is where he deals with primitive extensions. And he says that a primitive extension is solvable if and only, I mean, not if and only if, it's only in one direction. It says if a primitive extension is solvable, then its degree has to be the power of a prime. Okay, we will soon see a proof of this. So that is what is contained in the second memoir of Galva. So later we will also fix the prime L, and we'll look at extensions, look at L extensions, which means extensions of degree a power of L. And we will try to parameterize all solvable primitive extensions of f of degree L to the n. So earlier, what had we done? We had a field f and a prime which was called p earlier, but now today I'm calling it f. That of course doesn't make any difference, right? So earlier, let's continue to call it L, this prime. So earlier we had parameterized the set of all solvable extensions of f of degree p. Today, we still have the field f and a prime L, and we are going to parameterize all solvable primitive extensions of degree L to the n. So the earlier case is n equal to 1. Solvable primitive extension of degree L to the 1 is degree L. Then you don't even have to use the word primitive, because extensions of prime degree are automatically primitive. So earlier we had so the case n equal to 1 of what we are going to do today should give back what we had done earlier, right? Okay, so let's get started. So there's this notion of a now there's this notion of a primitive subgroup of a permutation group. What is that? So let's look at, so the permutation group is a permutation group of permutations, or the group of permutations of a finite set omega. So omega is any finite set. Everything is trivial if omega is just reduced to, is empty or has only one element. So let's assume that it has at least two elements. It has two elements or more. Then what is a partition of omega? A partition of omega is just a family of subsets of omega, none of which is empty, any two of which are disjoint, and the union of all of which is the whole of omega, right? That's what a partition is. It's a set of subsets of omega, each of which is non-empty, any two of which are disjoint, and the union of all of which is the whole of omega. That's a partition. And of course, any set omega has two partitions. There's a partition in which there's only one part, and that is, so it's a set of subsets. There's only one subset, and then that's omega itself. That's a partition, of course. Then, and there's another, so this partition is kind of trivial. There's another partition which can be considered to be trivial, which is the number of parts is equal to the number of elements in omega. And each subset, the subsets are just one singletons, right? That's a trivial partition of omega. So it's like, for a number, there are always two trivial divisors, one and the number itself. So for a set omega, there are always these two trivial partitions, the whole of omega and the set of singleton subsets of omega. Now, we are going to call a partition essential if the number of parts is strictly positive. I mean, no, not just strictly positive, but at least 2, right? Each part is non-empty, and there's at least one part which has at least 2 elements. Because if each part has 1 element, each part is just a singleton, that is a trivial partition, right? We have seen these 2 trivial partitions. So here is what an essential partition is. It should be, the number of parts should be at least 2. Each part should be non-empty, of course. That's true of any partition. Huh? And importantly, there's at least one part which has at least 2 elements. So now that's the notion of a partition of any set, finite set, and an essential partition is one which has these properties. I mean, it's not one of those 2 trivial partitions that I discussed. Now, then given this finite set, you have S omega, which is the set of all permutations of elements of omega, right? When you talk of the permutation group, it doesn't have to be permutations of the numbers 1 to n. Any finite set instead of 1 to n would do. You can talk of the set of partitions or the group of partitions, not partitions, permutations now. The group of permutations of any finite set, omega is denoted S omega. Now, if you have a partition of omega, we'll call it G stable. G is a subgroup, right? You have a finite set omega, you have S omega, which is the group of all permutations of omega. Then you have a subgroup G of S omega and a partition of omega. We'll call this partition G stable if G permutes the parts. And here's the precise definition. So what it means is that G just takes G permutes the subsets which constitute the partition, and of course elements within each subset. But it doesn't take, how do I say it? Yeah, I think it's reasonably clear what it means. So okay, one way of saying it is, if a group G acts on a set omega, then it acts on the set of subsets of omega. And it acts on the set of subsets of omega. And the set of partitions is a subset of the set of subsets of the set of subsets of omega. And so is this group of all essential partitions. Now, so this G will act on the set of essential partitions of omega. If none of those essential partitions is fixed by G, then you say that then you say that G is a primitive subgroup if there are no G stable essential partitions of omega. Now one can check that a primitive group is automatically transitive, but the converse is not true. It's true in prime degree, but it's not true in general. If prime degree meaning if omega has the number of elements in omega is prime, then to say that a subgroup of S omega is primitive is the same as saying that it is transitive. But otherwise, there are transitive groups which are not primitive. Okay, so these were just 2 definitions, very important definitions. And here is the theorem by Galva, which sort of generalizes that theorem that we had talked about earlier, this theorem here, right? So what does it say? Now, in order to understand it, I'll have to explain it a little bit. So you have a finite set omega that is fixed. It has at least two elements by assumption. S omega is the group of all permutations of this set omega. And then G is a subgroup of S omega, which is first of all solvable. That's the first hypothesis. And it is also primitive in the sense which I've just explained. So the theorem says that if G is both solvable and primitive, then there's a unique structure on omega of affine n space over FL for some prime L and some n. So let's try to understand this first. What does it mean for a set to have the structure of an affine n space over FL? And what is an affine n space anyway? So let's make this digression. Let's talk about affine spaces, right? So let's not do it in the most general sort of, I'll not do it in the most general setting, but let's do it in a fairly general case, which is you have an arbitrary field. Let's call it F, right? You have an arbitrary field F. And of course, you have the notion of vector spaces, finite dimensional vector spaces over your field F. Take some such vector space, call it V. Now, an affine space with over F with V as the space of translations is just a set on which this V acts simply transitively. Now, okay, so this is not difficult. Let me go back a little further and explain what it means for, or another word for this is a principal homogeneous space. Yeah, so here is my second reformulation of this notion. An affine space over F under the space of translations V is just a principal homogeneous space under V. So now we can go back and explain what is a homogeneous space, what is a principal homogeneous space, right? And for that, I don't need a vector space. I just need a group. A homogeneous space is, so now I have just a group, let's call it G. And I have a set on which this group acts. So G and a G set, what do you want to call it? Let's call it S. You have a group G and a G set S, which means there's an action of G on S, which means there's a homomorphism from G to the group of all permutations of S. Okay. And you know what it means for an action to be transitive. We have already been using this terminology, right? It just means that any two elements of S, for any two elements of S, there is an element of G which takes one to the other. For any two elements X and Y in S, there's an element G in capital G such that G of X is equal to Y, right? That's what it means for an action to be transitive. And when an action is transitive, the G set is also said to be homogeneous. And that's just another word for the same notion. And what is a principal homogeneous space? So it's a homogeneous space in which there's a unique element of G taking X to Y. So the definition is that given any two elements X and Y in S, there's a unique element little g in capital G such that g of x is equal to y. That's what a principal homogeneous space is. It makes sense for any group. Now, if your group happens to be a vector space over some field, after all, vector spaces are also groups, right? They're additive groups. So if your group happens to be a vector space over some field, then a principal homogeneous space under this group, under this vector space, is called an affine space over your field. So one way of thinking of an affine space is that it's really the same as a vector space, except that we have forgotten which point is the origin of the vector space. You sort of have all the other structure, but you don't have the origin. In particular, you cannot add two elements or 2 points in the affine space. 2 vectors can be added. Vectors are elements of a vector space. They can be added. But elements of a vector space, of an affine space, are called points. Points cannot be added. But if you have a point in your affine space and a vector in your vector space, a vector space under which this affine space is the space, a principal homogeneous space, then you can add this vector and that point, which means you can make that vector act upon that point. The element of the group acting on the element of the set. So that's what an affine space is. So now I've explained what an affine space is, and so what does it mean to give some set omega? Omega, let's come back to this. Omega here is just some set. S omega is a group of all permutations of that set omega. G is a solvable and primitive subgroup of S omega. Now, just because S omega has a solvable and primitive subgroup, you can give omega the structure of an affine space, n space, affine space, or n space is space of dimension n. And the dimension of an affine space is defined to be the dimension of the vector space of translations of that affine space. And what is the vector space of translations? It's the group under which this affine space is a principal homogeneous space. That group happens to be a vector space, so you call it the vector space of translations. So that action of an element of the group on the set, or the action of the element of a group is called, in this case, in this context, is called a translation by that vector. So there's a unique structure of an affine space over FL, right? Now, for some prime L and some N. So out of this omega and G, there are these 2 things given to you, omega and G. And out of these, you have suddenly produced a prime number L and some integer N, such that you have these inclusions. Okay, so what are these inclusions? G is here is G, right? And so that's G, and such that G is right. So I have to explain what N is, what AGL omega is. S omega we already know, right? G is what we have, and S omega is also something which we have. G is a subgroup of S omega. And I'm saying that if G is solvable and primitive, then it contains N and is contained in AGL omega. So I have to tell you what N is, what AGL omega is, right? Okay. Right. So now N So first of all, you have now you remember I'm saying there's a unique structure of affine n space over FL. So FL, of course, is the finite field with n elements, and if I have an affine L space, n space over FL, then I have some special permutations of this omega, namely the translations, which is, I mean, after all, if it's an affine n space, it's affine space, or if it's a principal homogeneous space under some vector space. And each element of that vector space gives you a permutation of this set omega, namely the translation by that vector. So N is the group of all such permutations. It's obviously a subgroup of S omega because I mean, every vector translation by any vector gives you a permutation of omega, right? So N here I've explained is the space of translations. And AGL omega is what? The group of all automorphisms or a group of all invertible affine maps of the affine space omega. So just as if you had a vector space V, then the linear maps or linear automorphisms of V would form a subgroup of the group of all permutations of V. Similarly, when you have an affine space, you have the group of all affine automorphisms of that space, right? So you can sort of think of it as all permutations of omega, such that when you translate, which sort of is it? Yeah, I think, yeah, right. So let's put it this way. What is AGL omega? AGL omega is a subgroup of S omega generated by two subgroups. The first subgroup is N. I've told you what N is. It's a space of all translations. And the second subgroup, to say what the second subgroup is, you have to choose an element of omega. Once I choose an element of omega, I can identify omega with the vector space under which it's an affine space. Okay, so remember I'd explained what a principal homogeneous space is. It's a G set, etc., right? So if I have a principal homogeneous space, S, and I choose an element X in S, then I get a bijection from the group G to the set S, which takes the identity element of G to this X. There's a unique bijection which respects the translations by G. I mean, G itself acts on itself by left translations, right? So the difference is between G and an arbitrary principal homogeneous space is that G has a special element, namely the origin, whereas an arbitrary principal homogeneous doesn't have a special element. But if you choose one, then of course it becomes the same as G. I mean, there's a canonical bijection of G sets from G to S, which takes the identity of G to the little x in the set S. So AGL omega is the subgroup of S omega generated by N and GL of omega. What is GL of omega? That for that you have to be a vector space, no, to talk about the GL. That's what. If I choose an element of omega, I get an isomorphism with its space of translations, but that space of translations is a vector space. So I can talk about the GL of that vector space, and that is what is meant. So I have, once I choose an element of omega, I get GL of omega inside S omega, and then I already have N. So these two generate a subgroup which I'm calling AGL omega. This definition of AGL omega does not depend upon, AGL omega as a subgroup of S omega does not depend upon the element which I have chosen to define it. Okay. Fine. So I've now explained everything which appears in this thing. So I've said if G is a solvable primitive subgroup of S omega, omega is any finite set which has at least two elements, and G is a primitive solvable subgroup of S omega. Then G has the structure of an affine n space over FL. FL is the prime field with L elements. L is a prime and n space for some n which is a strictly positive integer, such that it contains the space of translations, is contained in the space of all affine automorphisms, and that's it. This is what Galva's theorem says. This is Galva's theorem in the second memoir. Okay, so here's the proof. So it says, now G is given to me, and I take a subgroup which is a minimal normal subgroup of G.
Sir, what is the domain and codomain of affine maps?
Say it again.
Sir, what is the domain and codomain for affine maps?
Oh, this omega itself. The affine, no. These are automorphisms, affine automorphisms of omega. So they are maps from omega to omega. Okay, they are permutations of omega, but they are not arbitrary permutations of omega as a set. They are special kind of permutations. So, very concretely, if you have vector space, for example, if you have one-dimensional vector space, then what are the automorphisms of this vector space? It's A times X. X goes to A times X, where A is some scalar. And what are the affine automorphisms? It is X goes to AX plus B. So similarly, if you have a vector space of some dimension n, then you think of column vectors, column vector X going to AX plus B, where A is an invertible n by n matrix, and B is some column vector. So that's what an affine transformation is.
Okay, sir.
Right? Okay.
Yes, sir.
Okay. Good. So now it says that, so what is a minimal normal subgroup? Normal subgroups, you already know what they are, right? When is a normal subgroup minimal? So every normal subgroup always has one subgroup which is normal in the big group, namely the trivial subgroup. You have a group G, you have a normal subgroup N. The trivial subgroup of N is of course normal in G. But if that is the only normal, only subgroup of N, which is normal in G, then you say that N is a minimal normal subgroup. Minimal because there's nothing smaller which is normal in G. Okay, so of course any finite group will have a minimal normal subgroup, right? You take any subgroup, and if it is not minimal, then it has a subgroup which is normal in the big one, apart non-trivial subgroup, right? So you go to that one, and if that's minimal, then you are done. Otherwise, it has a subgroup which is normal in the big one, and you continue like this, and this has to finish. This has to come to an end because you're looking at finite groups. So take a minimal normal subgroup of G. Now, here is something which you need a little bit of group theory. Because your group G is solvable, N is going to be a vector space over some finite field L of some dimension n. So this n, the group n, will be isomorphic to Z mod Lz, direct sum Z mod Lz, direct sum, so on, up to some n number of times. This is something where you have to use the fact that this group G is solvable, and this I'm going to leave it as an exercise for you, or you can also look it up in any book on group theory, that if your group, in a solvable group, any minimal normal subgroup is isomorphic to Z mod Lz to the power n for some prime L and some integer n. Now, we also know that G is primitive. We have just used the fact that G is solvable, but G is also primitive. And n is, here is another bit of group theory, which is that if you have a primitive group, not only is it transitive, as I said earlier, but every normal subgroup is also transitive. That is, again, I mean, this is a bit of group theory, and you can look it up. So what have we got now? We have got two bits of information about this n. First bit is that as a group, it is isomorphic to Z mod Lz to the power n. And the second is that as a subgroup of the permutation group S omega, it is transitive. These are two things that we know about n. But we all, so if you have a commutative and transitive subgroup of S omega, then omega is automatically becomes an n-torsor. So what is a torsor? That's another word for a principal homogeneous space. Yeah, I should have introduced that word. That's shorter. I mean, it's just one word instead of principal homogeneous. So that's also just a little bit of group theory, which is, so you have some set omega, you have the group of all permutations of omega, and you have a subgroup of G or it's called n here. So let's call it n. And you have a subgroup n of S omega, which is required to have only two properties, that it should be commutative and it should be transitive. Then automatically, G, this omega becomes an n-torsor. Meaning, the action of n on omega, which is given to you because n is a subgroup of S omega, right? So this action is not only transitive, but it is simply transitive. That's what it means, right? Okay. So, and then not only is it some arbitrary action, but it's an affine action. So here are some sources from which you can look at this theorem, right? This is what Galva himself had proved, essentially. Maybe his terminology, of course, was not the same as this, but he had proved, let me see. Yeah, so what he had proved is, might be called a corollary of this, which is that if you have a subgroup of Sn, n little n, then its degree is the power of some prime. It is, where is it? Yeah, it's, do I say it's, anyway, it's a affine n space, so it's over FL, so the number of elements in omega is L to the n, right? Okay, so that was the theorem of Galva. So here is something that you might ask, there's a sort of converse to this, which is now you start with an affine space over, you start with an affine space over FL of dimension n, and let n be its space of translations, right? An affine space always has a vector space attached to it, which is the space of translations of that affine space, and under which it is a torsor, under which it is a principal homogeneous space, right? And that the translations are always a subgroup of the group of all affine automorphisms of omega. And now I'm taking a subgroup which is in between, a subgroup G. And the proposition says that it is solvable if and only if G modulo n is solvable. First of all, why can I talk about G modulo n? Why is G normal in, why is n normal in G? The answer is n is normal in G because n is actually normal in AGL omega, right? N is normal in AGL omega, and therefore it's normal in the subgroup G. So this G is going to be solvable if and only if G mod n is solvable. And when is G going to be primitive as a subgroup of S omega? It's going to be primitive if and only if, now I have this G modulo n module n, that should be a simple G mod n module. So what is a module under a group or under, so this let me explain a little bit. I'm not quite sure how many of you have already come across these notions, so I'm going into the very basics and explaining even the standard terminology. So let H be any group. H is any group. And what is an H module? And when is an H module called? Or FLH module. FLH module, what is that? And when is it called? Simple. So let's define that. So an FLH module is simply an FL vector space with a homomorphism from H into the GL of that vector space. GL is a group of all automorphisms of that vector space, right? In other words, it's a vector space over FL on which your group H acts by linear transformations, by FL linear maps. So that, or it didn't have to be FL, right? It could be any field K. So let's, instead of G mod n, let's take any group H, and instead of FL, let's take any group K. So what is a KH module? That's what I'm explaining now. So a KH module is a vector space over the field K with a homomorphism from my group H into the group of all automorphisms or K-linear automorphisms of the vector space, right? So that's a KH module. I mean, so KH can actually be thought of as a ring, and it's a module in the usual sense over this ring. So I'm not going to explain in what, how to make KH into a ring. It's called a group ring, or the algebra of the group H over the field K. So I'm not going to do this. Fine. But when is it called simple? So it's called simple. So when a group G acts on a vector space, yes.
Can you explain that why you are taking n is normal in AGL omega?
Now I didn't hear you properly. Say it again.
Sir, why you are taking n in normal in AG and omega? You have said that n is normal in AG and omega. So how can you say that? How can you say that n is normal in AG and omega? You are taking now.
Okay, so that is something that you just need to check. That n is
Okay.
normal in AGL omega. That's your question. Why is n normal in AGL omega? That's a question.
Yes. Yes, sir. Yes, sir. Yes, sir.
No. That is something that you just need to check.
Okay, sir. Okay, sir. Okay, sir.
Okay, so let's come back to this KH module. When is it called simple? So it is called simple. Again, you see, this is like a bit like the definition of a prime number or of a primitive extension. So a simple module or simple KH module is a vector space over the field K on which, of course, H is acting. But then when this happens, you always have two subspaces which are stable under the action of H, namely the whole of the vector space on which this H is acting. Let's call it V. Huh? So what do we have? We have a field K, we have a group H, we have a vector space V over K, and we have an action of H on this vector space by K linear maps. Now, there are two subspaces of this vector space V which are stable under the action of H, namely the whole of V and just the origin, the zero-dimensional subspace and the n-dimensional subspace where n is the dimension of V. These two are always stable under the action of H. Now, sometimes it might happen that some other subspaces are also stable. If so, then you say that V is not a simple KH module. But if there are no subspaces other than the whole of V and the origin, which are stable under the action of H, then you say that this V is a simple KH module. Is that clear? Right?
Yes, sir.
Yeah, okay, good. So now I've explained what simple means. G mod H, n is solvable if only if this K FL G mod n module n is simple. So why is n a G mod FL G mod n module? Because to make something into an KH module, you have to give an action. So to make a vector space V over a field K into a KH module, where H is a group, you have to give an action of the group H on the vector space V by K linear maps. Where is the action here? When did one specify the action? So the answer is that the action is sort of there. It's there because this N is a normal subgroup of G. So elements of G act on N by conjugation, or what are also called inner automorphisms, right? So an element little g of capital G will take an element little n of capital N into Gn G inverse. That Gn G inverse is again an element of capital N because N is normal in G. Okay, so that is the action of G on N. But what we want is an action of G mod N. Oh, well, it's actually an action of G mod N, or it descends to an action of G mod N because N acts trivially on itself because N is a commutative group, right? So in a conjugation or in a, conjugation by an element of n on n is, of course, the identity map. So n is the kernel of this action in some sense. So it's really an action of G mod n. Okay, so that's what this says, and here's the proof. It's not particularly difficult, right? So I'll skip it because I'm going very slowly today. And let's see. So you can read this proof here. Now, here is something which is very interesting. This is what happened. Yeah, it should work now. Yeah. So what does this say? Now, I have a finite separable extension E of f, and I have the notion of a primitivity for such extensions, right? This was discussed in section 1. So it's primitive in that sense of not having any intermediate extensions, if and only if this Galva group of E hat over f, this is always a subgroup of S omega, right? The group of all automorphisms, this Galva group acts on the group of all embeddings of all f embeddings of E into E hat, right? If I have an f embedding of E into E hat and an automorphism of E hat, then I apply that automorphism and I get another embedding. So this group of all automorphisms acts on the set of all embeddings. And one of the things that one knows from Galva theory is that this action is transitive. But what this statement is saying is that this makes, not only is it transitive, so G can be viewed as a subgroup of S omega as a transitive subgroup, but it's a primitive subgroup if and only if this extension is a primitive extension. That's what this statement is. Okay, so here's the corollary. If you have extension which is solvable and primitive, then its degree is the power of some prime. Why do I get that? That's basically a translation of this here. S is this omega is an affine FL space over of dimension n. So this omega has L to the n elements. That's all there is to it. Okay. So where do I go from here? So I've proved this. And so here's the crux. This number 8 and number 9 is what explains, 7, 8, and 9. So they tell you what we are doing in this lecture, and maybe also the next one, which is that we are fixing a field F, right? We are fixing a field F. We are fixing a prime number L and an integer L, and we want to look at all extensions of F of degree L to the n, which are solvable and primitive. This is the set we want to parameterize, of course, up to F isomorphism. Fix a field F, a prime L, a prime power L to the n, and we are looking at all solvable primitive extensions of F of degree L to the n, up to F isomorphism, of course, right? Now, how are we going to parameterize these? So the idea is that, so the first assertion is that if when I take the Galva closure of such an extension, E hat, I can basically recover E from E hat, maybe not up to F isomorphism. Now that's an important thing, right? Normally, this is not easy to give examples of, but it's something which happens. What happens? You can have a field F and two different extensions of F of the same degree, which are not F isomorphic. But when you take the Galva closure, you get the same thing. You get their Galva closures are F isomorphic. That can happen. Now, I can't give you examples straight away, but this is something that you can't rule out. Here, what is being said is that if your extension, I mean, one of your extensions is solvable and primitive, and then of course the other extension is also solvable and primitive, then of course necessarily they have to be, the degree has to be the power of some prime, but it cannot happen for solvable primitive extensions. What cannot happen? They cannot have isomorphic Galva closures without themselves being isomorphic. So in other words, the Galva closure E hat uniquely determines E. That's the first thing that we are going to prove. So we wanted to parameterize all such E, and we said this E, such E are uniquely determined by E hat. So now you have to characterize the kind of E hat which arise. Which extensions of F are the Galva closures of a solvable primitive extension of degree L to the n? So that is the next thing. So the thing is that we are going to classify them or parameterize them by pairs rho comma d. So that's what we describe next, right? What are rho comma d? So we'll do it slowly. So you have this E hat over F, and N is a minimal normal subgroup. We know that it's an FL space of dimension n, and it's a faithful simple module over this Galva group K over F, where K is the fixed field of n. So basically, yeah, I wish I had this pen which worked, but somehow it's not working. So what I have is, oh no. What I have is F here and E hat here, and G is this Galva group. Then I have N in G, which is a minimal normal subgroup. I take any minimal normal subgroup. Actually, there's going to be a unique minimal normal subgroup. And then I have this, see, it's not. I have this E hat. I have the fixed field of N. So the fixed field of this N. So that's being called K. And so what I get is So if I look at the Galva group of P F tilde over F, F tilde is the separable algebraic closure, then of course this Galva group of K over F is going to be a quotient of this Galva group of F tilde over F, right? Because it's this K is a sub-extension. Now, so you have the kernel of this quotient map, and then I have, what is rho E? Rho E is, so the conjugation action of this Galva group on this Galva group. This Galva group here is an FL space of dimension n. This Galva group here is what it is, and because this whole thing is Galva over F, I have an action of this over this. Okay, so that's basically what this pair consists of. The first component, rho F, is just it's not rho F, rho E is an irreducible FL representation of this Galva group of degree n with solvable image, and yes. Let me see. Okay, right. So yeah, exactly. So basically what I have is the first component, rho E, is an irreducible representation of the Galva group of F bar over F over FL of dimension n, and then I can take the fixed field under the kernel of this thing, and the so that's K. So this is a Z mod LZ to the n extension of this K, which is Galva over F. So yeah, maybe I'm not able to explain it without having a decent way to write it. Okay. So let's look at what this says. So suppose I have a pair consisting of, first of all, an irreducible representation rho of Galva group of F tilde over F over some FL space n of dimension little n. Okay, so that's the first component, rho. Okay, so, and what is the second component, D? So once I have a rho, this this D is, so once I have the first component rho, I get the fixed field K of the kernel of this rho. So D is an extension of this K, whose Galva group is isomorphic to n, and which is Galva over F as well. So this is what this pair consists of. It consists of an irreducible representation rho of the Galva group of F tilde over F on some FL space of dimension little n, and an n representation, n extension, a Galva extension with group capital N of the fixed field of rho. K is the fixed field of rho, D is that extension, which is required to be Galva over F, and such that, So when it's Galva over F, you get the conjugation action of this Galva group of K over F on N, and that should be given by rho. So it's quite somewhat of a mouthful, but it's not. Finally, it's not all that difficult, right? It's just okay. So yeah. So I'll take this up. I'll finish here today and explain a little bit more as to what we are parameterizing these things by. So the first, what we have is a field F, which is fixed. L to the n is a prime power. And here the set of all extensions of F, all extensions E of F of degree L to the n, and they are primitive. So the two things, the two properties that they should have are primitive. Yeah, this is bad. I mean, I don't know why it's not working. Yeah, so the two properties it should have are that it should be primitive and solvable. So this is the set we want to parameterize. And the statement that we are going to prove is that it can be parameterized by the set of pairs. The set of pairs rho comma t, where rho is an irreducible FL representation of the Galva group of F tilde over F of degree D, of degree n, right? Yeah, so let me just do this. So we're looking at pairs rho comma t, where rho is a representation of the Galva group of F tilde over F on some FL space of dimension little n, and that space is called capital N. The image of that representation should be a solvable group. And then once you have this rho, you get the field K, which is the fixed field of the kernel of rho. This K, of course, is an extension of F, right? And the second component, D, is an extension of this K, which has to have three properties, let's say. It should be Galva over K, and the Galva group should be isomorphic to N, meaning with a given isomorphism to N. Secondly, it should be Galva over F. And thirdly, once it's Galva over F, you have what is called the conjugation action of the Galva group of K over F on the Galva group of D over K. So that conjugation action should be given by the first component, rho. So what is the conjugation action? How can it be, I mean, what does it mean for it to be equal to rho? This is something that you should sit down and try to figure out. A conjugation action is there whenever you have an exact sequence like this. And where the kernel is a commutative group. Then this quotient acts on this by what is called conjugation. Basically, okay, so let me explain that thing, right? So let's look at this exact sequence here. This, I require this, okay, so I'm saying that if I have such an exact sequence, then this group acts on this, and that action is called the action by conjugation. In what way? I take an element here, I lift it to an element here. I can do it, of course, because this map is surjective, right? I lift it to an element here, and then I make it act upon this by conjugation. Of course, elements here act on this by conjugation because n is a normal subgroup of this group. Now, so that is supposed to give an action of this on this. Except that we made some choice in lifting. We started with an element here, then we chose a lift. So somehow you have to show that things don't, that lift doesn't matter. You get the same sort of automorphism of n for every, for each element of this quotient, the automorphism of n that you get is independent of the lift. That's what you need to prove. And that is true because this thing is commutative, because any two lifts will differ by an element here, and elements here act on n by, the inner action, the conjugation action of n on itself is trivial because n is a commutative group. Okay, so so that is the thing that we are going to discuss on Wednesday. Roughly speaking, it's a direct generalization of what is being done, or what was done in the course earlier, and what is being done in the tutorials. What is being done in the tutorials is the case of prime degree. You have a field F, you have a prime L, which is called P there perhaps, but that doesn't make any difference. And you are looking at extensions of degree L of this field F, which are solvable, in the sense that when you take the Galva closure, the Galva group is a solvable group. Here is a somewhat, here is the direct generalization, in the sense that we are now looking not at extensions of prime degree, but of prime power degree, but they are required to be primitive, which is automatic when the degree is prime, and they are also required to be solvable, as in the previous case of prime degree, right? So we are now looking at extensions of F of fixed prime power degree L to the n, which are both primitive and solvable. Those are the things we want to parameterize. And the result is that they are going to be parameterized by pairs rho comma d, where rho is an irreducible representation of this Galva group. In the case of prime degree, we were getting characters, and characters are nothing but irreducible representations of degree 1, right? So those characters get replaced by rows, which are irreducible representations of degree n. And the second component is an extension of degree L to the n of the fixed field of the kernel of rho, which is abelian of exponent L, which means that the Galva group is killed by L, and it's of order L to the n. So that means that, and it's abelian, of course. So that means that it's isomorphic to Z mod L, directs on Z mod L, directs on Z mod L, n times. Okay? So this extension D of K is abelian over K with a Galva group of exponent L. And it is also required to be Galva over F. Of course, you know that if you have a Galva extension of a Galva extension, it doesn't have to be Galva over the base, right? You have a Galva extension D of a Galva extension K of F. D doesn't always have to be Galva over F, but we require it to be Galva. So that's part of the that's the kind of pairs we are looking at. And not only do we require it to be Galva over F, as soon as it is Galva over F, there's this conjugation action of the Galva group of K over F on the Galva group of D over K, and we require this to be the same as the action rho, as the representation rho. This rho can be thought of as a representation of the Galva group of K over F on the FL space N, because N is, after all, a vector space over FL. It's a group isomorphic to Z mod L to the power N, so it's a vector space over FL. And this rho was a representation of, yeah, so it says the internet connection is unstable, and in any case, I have more or less finished for today, because I just wanted to introduce these pairs, and next time what will we do? Let's see. We will sort of, yeah, maybe just prove this statement, right? Yeah, that's right. So next, which statement are we going to prove? You're going to prove that the set that you want to parameterize is in canonical bijection with a set of pairs that I have been describing today. So that's what we are going to do next time. Okay, so I'll finish here, except that if there are any questions, you can ask them now. Are there any questions? If not, I'll stop here today and we'll meet on Wednesday.